Another lever calculation here. This is a third class lever. Let me read this problem to you. A medical patient uses a pair of 4-inch long tweezers to remove a wood sliver from a patient. The technician is applying, is applying 2 pounds of squeezing force to the tweezers. If more than 1/4 of a pound of force is applied to the sliver, it will break and become difficult to remove. So if you've ever used tweezers before, I'm just going to draw this and I'm going to erase it. Tweezers are something like this. Here's where the fulcrum is. You put one thumb here, put another thumb here, and you squeeze those together. That's the effort. And as you squeeze it together, then here the resistance gets pushed together. That's why it's a third class lever. You got the fulcrum, you got the effort, and then you got the resistance on the other end. So the picture for a third class lever, once again, they're all going to be the same. We have the fulcrum on one end, the lever extending. We have the force of the effort, the force of the resistance on the other end, and then your thumb, which is on the tweezer, is going to be pushing to give us the force of the effort. Of course, there's going to be a distance from the resistance to the fulcrum, and there's going to be a distance from the effort to the fulcrum. This is how every picture is going to look, an annotated, sketched diagram of a third class lever. Now the facts that we were given. A medical technician uses a pair of 4-inch long tweezers. So the distance of the resistance, I want to write this consistently how I did the other ones. I did force of the resistance, distance of the resistance, and then force of the effort and distance of the effort. It doesn't matter the order you write this in. I'm just trying to write it consistently as to not add confusion. So it said that the tweezers are 4 inches long. Well, we can see from the fulcrum to the end, which is the force of the resistance, that's 4 inches. That's the whole shebang. So 4 inches, 4 inches. To remove a wood sliver from a patient, the technician is applying 2 pounds of squeezing force. So the effort of the technician is 2 pounds. Effort force is 2 pounds. If more than 1/4 of a pound of force is applied to the sliver, it will break and become difficult to remove. If the resistance force gets to be more than 1/4 a pound, it breaks. So this has to be 1/4 of a pound or less. Force of the resistance, 1/4 pound. Hopefully you can see where this problem is going. We don't have the distance of the effort. Currently, could we figure out the ideal mechanical advantage or the actual mechanical advantage? The answer is we can only figure out the actual at this point, because actual deals with forces, and we have both forces. So the first question to this problem is going to be to find the actual mechanical advantage of the system. Let's do that. Question A. Find the actual mechanical advantage. The actual mechanical advantage is equal to the force of the effort, the force of the resistance divided by the force of the effort. Force of the resistance we see here is 1/4 of a pound. The force of the effort we see here is 2 pounds. We have a fraction divided by a whole number, let me show you how to simplify that. First of all, your pounds simplify. You take the numerator, which is 1/4, and instead of dividing it by 2, you multiply it by the reciprocal of 2. 2 as a reciprocal is 1/2. To multiply two fractions, you multiply them straight across, which gives us the actual mechanical advantage. 1 times 1 is 1, 4 times 2 is 8. As a decimal, 0.125. So you can leave it as a fraction. The mechanical advantage actual is 1 to 8, or as a decimal, it's 0.125 to 1. Those two things mean the same thing. Part B to this is going to ask, using static equilibrium calculations, calculate how far from the fulcrum the tweezers must be held to avoid damaging the sliver. So, in order to achieve static equilibrium, the moment of the resistance must equal the moment of the effort. To calculate a moment, you take force times distance. To calculate moment, you take force times distance. We have two different forces and two different distances. That's why we are subscripting with either resistance or effort. The force of the resistance is 1/4 of a pound. Quarter pounder, if you will. The distance of the resistance is 4 inches. Force of the effort, 2 pounds. Distance of the effort, we don't know. So we're trying to figure out. On the left, multiplying a fraction, 1/4, times a whole number 4, you multiply the whole number times the numerator, that's 4 times 1, which is 4, then divide by the denominator, which is 1. 1/4 of 4 is 1. 4 times 1/4 is 1. So we get 1 inch-pound on the left. On the right, nothing to multiply. We get 2 pounds times the distance of the effort. To get distance of the effort by itself, we divide both sides by 2 pounds. On the right, we then have the distance by itself. On the left, you can cancel the pounds out. So we're left with 1 inch divided by 2, which is going to be 1/2 of an inch. Or 0.5 inches if that is how you're raised.